9.9 Lesson 1, Representation of Functions by Power Series. We have one objective for today. And our objective is you'll be able to find a geometric power series that represents a function and find its interval of convergence. As we look at the three examples for today, you'll know what this means. And I will explain what it means for a geometric power series to converge to the function that it represents on its interval of convergence. So vocabulary for today, geometric power series, we've already seen radius of convergence and interval of convergence. So here we have Theorem 9.6 from section 9.2, convergence of a geometric series, and we're reviewing this because it's relevant to what we want to accomplish today. A geometric series with ratio r diverges if the absolute value of the common ratio is greater than or equal to 1. If the absolute value of the common ratio is less than 1, greater than 0, then the series converges to this sum. So find the sums below for each of these two geometric series. So you just use a over 1 minus r. That's a. So I have a over 1 minus r. r is 1/2, so I have 1 minus 1/2. And that is equal to 10. For the second one, we have a over 1 minus r. r is negative 1/5. So 1 minus negative 1/5 is 1 plus 1/5, which is 5 over 5 plus 1/5, which is 6/5. And when you divide, you get 5 over 2. Our first example for today is number 2. Find a geometric power series for this function which is centered at c is equal to 0. How do we know that the function is centered at c is equal to 0? Well, if you look at this part, you don't have x minus any particular number. So that's how you know that the function is centered at 0. Well, we're going to... We want our geometric power series for this to be this function to be centered at c is equal to 0. So let's see how that ties in with our objective. You'll be able to find a geometric power series that represents a function and find its interval of convergence. To help us accomplish our objective, we will use Theorem 9.6, convergence of a geometric series. Why is it that this particular function or functions of this type are suitable for representation by a geometric power series? The reason is the function as written closely resembles the sum of a convergent geometric series that we learned about in section 9.2. You can see that the numerator is 4 and the denominator is 5 minus x. So it closely resembles a over 1 minus r. There are some differences. Actually, there's one difference. That one difference is the following. You can see that in the sum of a convergent geometric series, the denominator is 1 minus r, but here we have 5 minus r. So if I want to represent this function with a geometric power series centered at 0, I have to algebraically manipulate this function so that it will fit a over 1 minus r exactly. In other words, I need to somehow have 1 in place of the 5 without actually changing my function. That objective can be easily accomplished by multiplying our function by a form of 1. So if I multiply the numerator by 1/5 and the denominator by 1/5, I'm essentially multiplying my function by a form of 1. And 1 is the multiplicative identity, so it won't change my function, but it will just have it in a different form. So 4 times 1/5 will give me 4/5 in the numerator, and in the denominator I will have to distribute the 1/5 to each of the two terms that I have in the denominator. 5 times 1/5 will give 1, and x times 1/5 will give x over 5. So I'll have minus x over 5. So what I've done is I have algebraically manipulated my function without changing it. So it's the same function that I began with, but now it is in the form a over 1 minus r. So I'm going to use the theorem 9.6 about convergence of a geometric series, and I'm going to use it in this direction. I will start with a function that resembles the form for the sum of a convergent geometric series, and I will use that to help me write a geometric power series that would represent this function on its interval of convergence. So what I'm going to write is this is going to be represented by a geometric power series, and it's going to be from n is equal to 0 to infinity. And what would I need to have? I need to have a times r to the n. And what is a? A is whatever I have in the numerator. So a is going to be 4/5. And what is r? Now that my denominator is in the form 1 minus r, all I need to do is look at the x minus 5 to know that that is my common ratio. So I have x, not minus 5, but x over 5. That's my common ratio. And I will have that to the n power. So this is the geometric power series that would represent the function f on its interval of convergence. And what is the interval of convergence for this geometric power series? What do you look at? You look at the absolute value of the common ratio, and you want to make sure that that absolute value of the common ratio is less than 1. Now, if it's equal to 0, I will still have a series that converges. And in fact, what would it converge to if this absolute value of the common ratio is equal to 0? Well, then I would go back to the original function. What happens if x is equal to 0? Then you will have f of 0 is 4 over 5. If you make x equal to 0 here, you will have 0 to the n. And when n is equal to 0, we agree by convention that this particular part of the description of the nth term will be 1 when n is equal to 0. If x is 0 and n is 0, we agree that this particular part of the nth term will be 1. So I'll get 4/5, and that will be my sum if x is equal to 0. So you don't need to worry about that. So you just need to concern yourself with the absolute value of the common ratio between being less than 1. And if you rewrite that as a compound inequality, you'll have the following. You'll have x over 5 is less than 1 and greater than negative 1. And if you multiply both sides, or if you multiply all three parts of the compound inequality by 5, then you will get your interval of convergence, which will be x is between negative 5 and positive 5. So what does all this mean? This simply means that our infinite geometric power series that we have written here will be an exact representation of our function f on this interval of convergence. So for x values that are between negative 5 and positive 5, our infinite geometric power series will not be an approximate representation, but it will be an exact representation of the function. But the condition is that you need to have your infinite, your geometric power series has to be infinite. However, if you have a partial sum of it, for example, if I have the geometric power series, but I don't have an infinite geometric power series, but I have a partial sum of it, and where n goes from 0 to 3, meaning I have a sum of 4 terms, or my fourth partial sum, because it's not infinite, it would only approximate the function. And it would be approximating the function on this interval of convergence. The more terms I have in my partial sum, the better the approximation will be. And if I have an infinite sum, this geometric power series will be an exact representation of the function f on this interval of convergence if I have an infinite sum. To help you see this, I have gone ahead and made a graph. I have made a graph that it actually has 3 graphs. It has the graph of the function f of x. It has the graph of the function that you would get when you consider the fourth partial sum of this infinite geometric power series, the sum of just the first 4 terms of it. And I also have, with the upper limit of summation equal to 4, which would be the fifth partial sum. And each of those partial sums will be an approximation for the function f on this interval of convergence. The greater the number of terms in the partial sum, the better the approximation will be. And if you have the infinite geometric power series, it will represent the function exactly. So this is the graph of the function f. It's in red. So you can see the graph of the function f in red. You can see that the graph of the function f has a vertical asymptote at x is equal to 5. And in blue, I have the graph of the fourth partial sum of the geometric power series that we found for f. So in blue, we have the graph of the fourth partial sum. And here's the graph of the fourth partial sum. And you can see that this particular graph closely approximates the graph of the original function for x values that are between -5 and +5. And as an extra comparison, I have also gone ahead and graphed the fifth partial sum of the geometric power series for the function. You can see that what we have here in green is the graph of the fifth partial sum of the geometric power series that represents the function. And the green graph is also a good approximation of the function on the interval of convergence for the geometric power series. And the more terms you have from the partial sum, the better the approximation will be. And if you have the infinite geometric power series, then it would be an exact representation of the function. I'd like to demonstrate what that means. What does it mean to say that this geometric power series is an exact representation for the function? Of course, the infinite geometric power series. Let's look at that. So what does it mean to say that our function is represented exactly by this geometric power series on this interval of convergence? Let's revisit theorem 9.6, convergence of a geometric series. We know that if the absolute value of the common ratio is less than 1, the geometric power series, or any geometric series, will converge to the sum a over 1 minus r. So using that, I can represent the sum of this convergent geometric power series. It converges for these values of x with that formula. I can write a over 1 minus r, 4/5 over 1 minus r. And of course, we know that this is algebraically equivalent to our function. And again, it is in fact algebraically equivalent to our function. All you would have to do is multiply what we have here by 5 over 5, which is a form of 1, and 4/5 times 5 is 4, and in the denominator, if you multiply the 5 to each of the two terms, if you distribute the 5, you get 5 minus x. So in fact, because of that, if you were to evaluate the function f at any x value from this interval, for example, let's say you want to find what f of 2 is. What is f of 2 equal to? F of 2, if you use the function, will be 4 over 5 minus 2. 5 minus 2 is 3, so this would be 4/3. Now, if you wanted to evaluate the geometric power series that represents the function on this interval of convergence at x is equal to 2, you would also get 4/3 because this geometric power series is an exact representation of our function on this interval of x values. So again, how would you evaluate the geometric power series at x is equal to 2? You just use the formula from the theorem to find the sum of a convergent geometric series. So you would substitute 2 for x, and because the absolute value of the common ratio would be 2/5, which is less than 1, you can find the sum of this geometric power series at x is equal to 2 simply by doing a over 1 minus r. And if x is 2, the common ratio would be 2/5, and you would have 4/5 divided by 1 minus 2/5 is 3/5, and when you do the division here, you will get 4/3. So that's what it means to say that our function is represented exactly by this infinite geometric power series for these values of x. And as I showed you with my graph, if you consider partial sums of your geometric power series, then you would have approximate representations. But the infinite sum would be the exact representation for the function. So here we look at a second example, number 10. Find a geometric power series for the function centered at c is equal to 0. And our function is h of x is equal to 1 over 2x minus 5. So our goal is to use the theorem that we learned in section 9.2 for the convergence of a geometric series. And to do that, we need to rewrite our function so that it fits the form a over 1 minus r. So we have to do some algebraic manipulation. And the first thing that we can do is the following. So we can just write for the denominator negative 5 plus 2x. Because I need to have a minus r. And of course, the x will be a part of the common ratio because we want to write a geometric power series. I need to have 1 minus r. Right now we have a plus. An easy way you can deal with that is to multiply the numerator and the denominator by negative 1. So when you do that, you're multiplying the function by a form of 1, so you won't change it, and you'll have negative 1 over, and then you will have to distribute the negative 1 to each term that you have in the denominator. So that will give you 5 minus 2x. So we're closer to where we want to be. We want to be over here. We want to have the form a over 1 minus r. So we begin with the plus sign, now we have a minus sign, but I need for this number here to be 1, because I need to have a over 1 minus r. Again, that is easy to do. Just multiply your function by a form of 1. We will multiply our function by 1/5 over 1/5, which is a form of 1, and that would give negative 1/5 in the numerator over, when you distribute the 1/5 to the 5, you get 1, and when you distribute the 1/5 to the minus 2x, you get minus 2x over 5. So now you can see that our function h has been rewritten so that it is in the form a over 1 minus r. And once you have it in that form, you know that this is a, and you know that what you have here is r. So you can easily represent this function with a geometric power series on its interval of convergence. So I'm going to do that right here. So this function is equal to this infinite geometric power series. A would be negative 1/5, and r would be what you see right here. It would be 2x over 5, and you're going to have to raise that to the n power. So the next question is, what is the interval of convergence? In other words, for what values of x will our function h be represented exactly by this geometric power series? What are the x values for which this equality is a true statement? So to determine that, I'm going to find the interval of convergence for this geometric power series. And all I have to do is look at the absolute value of the common ratio and set that less than 1. So I will write my absolute value inequality and then write that as a compound inequality, and then multiply all three parts of the compound inequality by 5 to give me negative 5 is less than 2x is less than 5, and then divide each part of the compound inequality by 2, which gives me my interval of convergence for this geometric power series. In other words, this geometric power series is an exact representation for the function h of x for these values of x. And this is our geometric power series for the function centered at c is equal to 0. You can see from the geometric power series that I'm not subtracting anything from x, so that's what it means that it's centered at 0. Now we look at number 8, and the instructions are find a geometric power series for the function centered at c is equal to 2. So this is different from the first two examples in that in the first two examples, the geometric power series that we looked for were centered at c is equal to 0. But here, we want a geometric power series that is centered at c is equal to 2. And the way you're going to accomplish that is you've got to make sure that when you write your geometric power series, your common ratio will have, well, what do you need for your common ratio so that your geometric power series will be centered at 2? Well, you need to have something in there that has x minus 2 in it, so that we will have a geometric power series that is centered at 2. So you've got to have something like this for the common ratio so that you will have a geometric power series for this function that is centered at 2. So what do we need to do to make that happen? Well, we've got to somehow sneak that in there by doing algebraic manipulation. Sneak that in there is just a figure of speech. It's not really sneaky or anything, but maybe you have to be a little bit creative. So now let's see how we can accomplish that. So the general principle in mathematics is that they are inverse operations and they undo each other. So for example, let's say you have $5 and your friend gives you $2, so now you have 7, and then he changes his mind and he takes $2 back. So you're back at $5. It's like nothing happened, right? So it's kind of like that idea. You can add and subtract the same quantity and it wouldn't change anything. So here we're going to take advantage of that. So what we want is to have x minus 2 so that we will accomplish our objective of having a geometric power series for the function that's centered at 2. And here's what we're going to do to make that happen. So look at the x that I circled in red. I'm just going to put parentheses around and then start parentheses. I'll write the x that I circled in red, but I want to have x minus 2, so I'll subtract 2. However, I just changed my function. Why did I change my function? Well, if you distribute the 2 to the x and you distribute the 2 to the negative 2, you will actually have 2x minus 4 minus 1. But I didn't have that before. So what did I introduce that I didn't have before? I introduced subtracting 4. So to compensate for that, I need to do the inverse operation of adding 4. And all of this is happening in the denominator. So that is the first most important step that you need to do if you want to find a geometric power series for the function centered at a c value that's not 0. You've got to get that x minus c into your function so that that will become a part of the common ratio for your geometric power series, so that it would be centered at, in this example, 2. But as we just saw, you can accomplish that with this algebraic manipulation, but you have to make sure to compensate for what you just did by doing the inverse operation, so you keep your function exactly the same as what you began with. The remaining steps are the same as what you saw for the first two examples. We're just going to work with what we have here and try to write it in the form a over 1 minus r by doing some algebraic manipulation as needed. So we're going to write f of x is equal to, in the numerator we have 3, and in the denominator, when you combine these two constant terms, negative 1 plus 4 will give us positive 3. So we have 2 times x minus 2 plus 3. Again, what is our objective? Our objective is to make our function, rewrite our function so that it's in the form a over 1 minus r. And again, for the common ratio, we want whatever has x to be a part of our common ratio so that we get a geometric power series. So the next step is for me to do the following. I will just write this as 3 over, and I will switch the two terms that I have in the denominator. I'll write the 3 first plus 2 times x minus 2. So now I have the term that has x in it where the common ratio should be in a over 1 minus r. The last thing that I need to do, well, I need to do a couple of things. I need to have 1 minus r. So right now I have plus, so I need to do something about that. And then I need to have 1 minus. Right now I have 3. It's pretty easy to get this to be a minus. You can just subtract the opposite. So 3 minus negative 2 times x minus 2 is the same as 3 plus 2 times x minus 2. So we've gotten the minus there, and the last thing that we need to do is to make sure that what we have here is a 1, so that we have 1 minus r. And that can be done easily by multiplying by this form of 1. 1/3 over 1/3 is 1, and that will give us 1/3 in the numerator, and in the denominator, when we distribute the 1/3 to what we have here, when we distribute that, 3 times 1/3 will give us 1 minus negative 2 times x minus 2 times 1/3 will give us negative 2/3 times x minus 2. And as you can see, we now have our function written in the form a over 1 minus r. So now we're able to represent our function with the geometric power series using the theorem that we learned in section 9.2 about the convergence of a geometric series. Before continuing any further, I'd like to correct an error. 3 times 1/3 is 1. So in the numerator here, I should have 1. A student caught that. Thank you. All right. So now we're ready to go ahead and complete our problem. So we did some work. I'm going to erase the intermediate work so that I will have more room to complete my problem. So this is all the steps that we had just completed to rewrite our function. And ultimately we were able to rewrite our function as 1 over 1 minus negative 2/3 times x minus 2. Now it is in the form a over 1 minus r. So we're able to represent our function with a geometric power series. So now we can write this is equal to the geometric power series from n is equal to 0 to infinity of a is 1, so I can either write 1 or not write anything, times r to the n. And this is, of course, r. So our r value is negative 2/3 times x minus 2, all of that to the n power. And if you choose to, you can work with what you have here and rewrite that in an equivalent form, or you can leave that as it is right now. So the last thing that we need to do for this problem is to find the interval of convergence. I should have written that in the instructions, so we're going to add that to the instructions. We want to find the interval of convergence for this geometric power series. In other words, for what x values will this geometric power series represent our function exactly? So to find that, you're just going to use the fact that the geometric power series will converge when the absolute value of its common ratio is less than 1, which is what we have here. And again, to give myself some room, I'll go ahead and erase that. And now I'm able to complete the problem on the right side of the screen. So we have the absolute value of the common ratio needs to be less than 1. And this is what you would have. So you take the absolute value of the common ratio. The absolute value of negative 2/3 is 2/3, so I just write that. And then I have the absolute value of x minus 2. That has to be less than 1. So I write this absolute value inequality as a compound inequality here. Multiply all three parts by 3 over 2, which gives me this compound inequality, and add 2 to each part of the compound inequality, giving me the interval of convergence. In other words, for x values between 1/2 and 7 over 2, this geometric power series will represent our function exactly, and of course, this geometric power series is centered at c is equal to 2. So we found a geometric power series that exactly represents our function centered at 2, and it would exactly represent our function for these values of x. What is the purpose of centering our geometric power series at 2 or some other value of x? The purpose is, depending on what the center of your geometric power series is, that center of the geometric power series will determine what the interval of convergence will be. So depending on where you want this function to be represented exactly by your geometric power series, you need to choose the center to be a particular value so that the geometric power series will be an exact representation of that function for those values of x that you desire. So today we looked at some examples for finding a geometric power series that represents a given function centered at a particular c value, and then we found the interval of convergence for that geometric power series. In other words, the x values for which the geometric power series represents the function exactly. And depending on what x values you want to be what x values, depending on the x values for which you would like the geometric power series to represent your function exactly, you would have to work with where you want your geometric power series to be centered.